Alright, this next drill is on electromagnetism again, and this time we're just going to be looking at these questions, and I'm going to pick the key equation that should solve it. I'm not really going to solve it, I'm just going to name the equation that I have to use. So vector field is given, and we're evaluating this at the point 1, 1, 1. So I mean, one should probably be solving this equation. I think that's kind of a stupid question. So let's try the next one. A point charge Q is fixed height A above an infinite grounded conducting plane from the force acting on the charge. So that would be like QE at 0, 0 A, where E equals negative delta V, and V is equal to 1 over 4 pi epsilon naught. Q over R plus Q over R minus. This should be like a minus. I'm pretty sure that that would solve this. So we'll go with that. And then for question 3, potential in a charge-free region satisfies this. Given that the potential is finite at the origin and vanishes at infinity, which coefficients must be 0 and y? What the hell? Well, this is r goes to 0, meaning BL? And then r goes to infinity makes AL go to 0. Like, that's so easy. Okay, next one, 4. Uniform polarization fills a solid sphere of radius r. Find the bound volume charge density, which is P. Right. In this particular equation, in the negative sign, the bound surface charge density, so that's P dotted with n hat, equals this. And this should probably be an r hat, specifically. And result the electric field inside. How are we going to find the electric field inside? I think that it would be equal to, I think it's equal to the polarization field of epsilon naught, but I'm not entirely sure. We'll have to see about that. And then for number 5, says that outside a localized charge distribution, the potential is measured to be this. Then find the monopole and dipole moments of the distribution in terms of A and B. What? What? I have no idea what that's even asking, but this is, I mean, A is for the monopole, and B is for the dipole. Well, so I don't know whether these are the correct answers, but we'll go ahead and we'll go ahead and do this. Show them the response, and we'll see how this goes. Yeah, sounds good. Sounds correct. I guess this is d over epsilon naught. But how are we going to find d? I thought it was d plus p. Let's just double check. D minus p over epsilon. Mm, but there were no free charges, so this is be negative p over epsilon. I think let's try this then. So for one, we have point charge is located at the center of a grounded conducting spherical shell. Denoted as A, denoted as B, find induced surface charge densities on both the inner and outer surfaces. Induced surface charge densities. So here is the Q, and here we have A and B. Find the induced surface charge densities on both the inner and outer surfaces. Electric field. Well, this is kind of more of a visual diagram because here we have to have negative Q here and then a plus Q here. We'd have to use like E 4 pi r squared equals Q over epsilon. Because there would be an induced charge here and then an induced charge. Well, this is a grounded conducting sphere, so it's going to rearrange the charges here. It's still neutral, but it forces this to like be I think that would be the correct answer on that. 2. In a charge-free region bounded by a long cylindrical surface of radius r, potential is E naught cosine 3 phi. Find the potential everywhere inside the cylinder. So from this, we can see that L equals 1. Say I'm a little bit confused here. I think M equals 3. We're doing Like, we're using the Bessel here, I guess. What's the solution? Isn't it like A cosine plus B sine? I'm not entirely sure. I'm gonna have to like review that real quick. It should be coming from this stuff. So I guess we multiply it by both. We do that. So we kind of need two parts to this one. It's kind of like A r to the m plus B r to the negative m. And then we have to do this, where m equals 3. And B equals 0. I think that should set that up relatively well. Let's go to the next question. Reduce. Grab this, up a bit. Question 3. Localized charge distribution has vanishing monopole and dipole moments. Okay, so that means that Q0 equals 0, P equals 0, but a non-zero quadruple moment tensor. Oh my god. This is Q3, right? The leading far field expression for the electric potential in terms of Qij. I don't know how that's supposed to work, but I will go Q3 over R to the third. And I think that here we have to do PL. I'm guessing this is P3. At the leading far field expression. What is that even referring to? Far field expression. So looking at this, quadruple? It's Q2, P2. My bad. Q2, P2 divided by R to the third. But Q2 is like this weird integral. So that's really the key for this. For the third, and then we have the PL cosine in there. I guess P2, P2. Wait, what? It should be squared then. And P2. And then D3R. Right? Check. Oh, the P isn't in there. Gotcha, gotcha, gotcha. So the P is not in there. And we'll just do this. Okay, that was question 3. Question 4. Linear dielectric slab. Xe completely fills the region. The region Z is less than 0 is vacuum. Uniform electric field exists far above the slab. we kind of have this region of Z that's filled with dielectric, and we have this far field that's E naught Z hat. Find the electric field in all three regions. Here's B, here's 0. This one's gonna be hard. No, I don't really know what we're supposed to do here. Um, oh my lord. Let's see if we can get some hints from this sheet. I guess we might be able to do something like this, like find the voltages from the bound charges. But no, that's just like a linear dielectric. Let's go down here. Here are the equations. So we have to remember that P equals this. Okay, and hmm, it's not really hard. I have no idea. Let's put some question marks. Alright, so the last question here, and then we'll look at some answers. Question 5. Which field satisfies this stuff? Prove the uniqueness of the electrostatic field in a volume given the potential on the boundary. Are you serious? Prove the uniqueness of the electrostatic field in a volume given potential on the boundary. VR minus some other V. Integrate that using these relations. Man, I don't know. These are okay. Those are really hard questions. I think we managed to get like the first couple or something. So let me see what the key equation is. First one was pretty easy. We don't need to know the results. This one, yep, we got that solution correctly. Fine. Quadruple only. This tensor form is this. Axisymmetric. You know, that tensor form thing is a little bit crazy. The electric slab between fields. Here we have this, and then we're supposed to go D equals this, and then somehow come up with, let's find, this one's really, really hard. It's not D. So I guess they want us to do like D minus D, D out minus D in equals the surface charge. I guess we have to set E out equal to E in, but this is the tangential, not the normal. But how are we supposed to like even say this? These are the theta versions. Yeah, it's just really confusing. Okay, and the last one here. Man, yeah, the last one is insane. Hopefully we don't get these kinds of questions on our exam. But yeah, these are some hard drills. But hopefully you guys have a good night.